Thanks for the Shelly. So yeah, the title is pretty long, so kind of shorten it as like low mass stars and exoplanets with KPIC. And so I'm postdoc at Northwestern University. Before I get started, I want to acknowledge this science is enabled by the huge KPIC instrument team across different institutes, and also appreciate all the fundings from NSF, JPL, Hudson Simons Foundation. And just a very exoplanet 101 overview of why we care about exoplanets in general. That's because we can directly study their atmosphere. And for example, these three systems are HI 8799 planets and 51 Area B, and then PDS-70 B and C systems. These three systems are kind of like showing case of pretty young exoplanets. They're away from the pulsar in terms of like a few to dozens of AUs in separation. That's very different from the hot Jupiters. So we can study them and formation evolution in different space scale and then different atmospheric properties, because hot Jupiters is pretty close to stars. There's irradiation. Direct imaging exoplanets are kind of probing into different formation in here. And in terms of technology, this is kind of showcase of how we can do with the high resolution spectroscopy. So first, we can resolve the lines, and then we can measure the radial velocity, which means we can measure the orbit and also potentially see the binaries or exosatellites, for example. And in terms of the line broadening, because of the spin, we can study their angular momentum evolution. In terms of different line ratios of balances, for example, we are targeting in say CO bandhead at 2.3 micron, and we can measure abundance of C-to-O ratio, and that's important in studying the formation evolution in terms of exoplanet. And KPIC, thanks Luke's introduction, but here I want to just emphasize how we do in terms of running direct imaging spectroscopy. So here is the example of 8799 planet system, and then we're pulling 1 to 4 fibers onto a planet that's in red, and then all of these 4 fibers are illuminated and via single mode fibers to fit onto a Keck spec. And then these 4 traces are illuminated, and one of the traces has a planet line, and the rest have the also spectral contamination. And also, as Luke mentioned, KPIC is facilitized, so feel free to propose for KPIC science. And we also have like a YJH band and L band capability with recently LFC-CON. And KPIC has a lot of detections already in terms of direct imaging. It's about 30 low mass companions that includes a benchmark round dwarfs, also gas giant exoplanets. And just in 2024, we have a lot of like papers being published, accepted. And then in terms of direct imaging side, there's a lot of benchmark system in addition to abundance survey by Jerry Swan. And in hot Jupiters, we just heard Luke's talk, and then the very last line is not in prep, is submitted this morning. And also want to like kind of highlight Ben Sapia will be giving a KPIC / high spec talk tomorrow, and then Thursday will have the poster kind of also we can ask her about her talk about work about RxJ0342B. And I want to focus on one system today first. So this is the PDS-70 B and C system. This is one of the most famous exoplanet system because it's the only protoplanet system with a natal disk observed today. And this is the pretty young PDS-70 A star. So the age is 5 million years old. And then C-to-O ratio is being inferred into as a 0.4, which is around solar metallicity or slightly subsolar. And both B and C are detected with H alpha emission. So that means there's an ongoing accretion around these 2 planets. And from ALMA, we know that this C-to-O ratio is more than 1. So if we can measure the C-to-O ratios of planets B and C, and it will be important to study their formation evolution. And there is recently, in just this year in May, after a KPIC phase 2.5 upgrade, we just kind of pointed at PDS-70B, and then we have a pretty relatively weak detection in terms of CO and then CO plus water detection. So this is how we usually claim a detection by running a molecular template. So in this case, the left is a CO template across different velocity. If there's a peak near the expected velocity, and then we usually claim a detection. And then we show sigmas of 3 and 4 roughly in these two molecules. And we attempted to constrain their spin and radial velocities. So the RV is actually not the same as a whole star because we also measure the whole star RV and the same epoch because we also have the on-axis star spectrum. In terms of spin, the posteriors, so this is the fit by the BD cell model, and the spin is actually stacking. If you look at the corner plot, this is like stacked on the lower end, and then we also try to test if there's the no spin scenario, it actually favors more. So we don't think we detected the spin, and this is expected. And at 5 years old, the planet is still fluffy, and this is also validated by a lot of ground work. When they are pretty young, they're actually they should have pretty like minimum velocities. But there's some caveats I can ask me later. And we also attempted to constrain the C2 ratio. So this is by using the Petty-Retchen package. But here because the SNR is relatively low, we only use the NORA pressure temperature profile to kind of fit the data. So we're mostly just fit the C2 ratio and methodicity here, and then we are measuring C2 of definitely less than 1, and then we think, so in this case it's about 0.4, and definitely less than 0.6 or so. And methodicity is consistent with the solar. In some of other retrieval rounds, we have like slightly super solar, but you can see uncertainty is basically consistent across all the scenarios. So, but what is interesting is because this is seemingly inconsistent with the ALMA disk constraint. So ALMA disk has the C2 ratio larger than 1. So how can we say compensate or explain this? So if the disk is has been separated or kind of enhanced in terms of pollen, and then the planet is formed afterwards, and then we expect actually C2 more than 1. But if the planets are formed like before the carbon is enriched in the disk, and then we're expecting more like a star or slightly enhanced C2 ratio. So there's a modeling result by President in 2023 by considering these two scenarios and have these two predictions. So this is one of the important constraints we can place here. But we have to also emphasize this is still relatively noisy data. So we'd love to take more data next year, unfortunately, because it's not up right now, to kind of validate and kind of constrain our balance measurement. And right now, I want to move on to this spin a little bit. So this is non-detection, but we're thinking maybe there's a mass dependency in terms of the spin. But unfortunately, we did not see. This is the fractional breakup velocity versus different masses that KP is sensitive to, plus some of the free-floating like ground low mass stars measurements. And we don't see a clear trend in terms of the rotation. So I'm gonna skip this because there's some other like real features that we're seeing here. And here's some of the background as like why we care about this, the spin in general. So in terms of the low mass stars, I'm talking about sunlight star all the way down to M dwarfs. When they form, they're fluffier and then they contract to them in sequence. So assuming angular momentum conservation, they basically just spin up. But over time, they release kind of the angular momentum through magnetized winds and flares, and due to several magnetic activities. That's well known for FGK stars, and then M dwarfs have similar features, but it's like there's a wider spread, but there's also spin down trend for M dwarfs. But for very low mass objects, I'm talking about 1 to 80 Jupiter masses object, they are mostly spin up over time. And the explanation is because their atmosphere are kind of like dissociate when it's too cooler with the rotation, with the spin down mechanism. So in Johannavas in 2022, they found the basic spin down, but you can see there's in terms of masses, for very low mass, which is in the red, they're not sensitive to the very low mass and pretty young age. So this is not validated within this messaging and its age. And then, so this is actually pretty complementary with the VSI survey. So if we look at just the left plot, this is kind of the other survey that published earlier this year. This is from STC Apogee. So if you look at several clusters members in terms of V sign, it actually shows a general spin down relation, although the sample is quite small. And if we kind of compare with kind of benchmark measurement from KPIC, that means we have the age, we have the masses for most of them, and then they show like a general spin up to like 50 joule masses. When it's like more than 50 to say down to hydrogen mass per nm, we start to see some of the slow rotators and the end of it. So so this is kind of like complementary to what the rotational pairs could improve in the past. So finally, I want to have some key takeaways, and hopefully you remember what I mentioned about PD70P. C2 ratio is disfavors of like more than 1, and we actually constrain the less than 0.6, and there's no spin, and then the angular momentum history is different and different mass spin, and we kind of tend to see the masses between 6 to 50 joule masses are kind of spinning up and kind of adding to what rotation pairs are sensitive to. And if you're curious about other KPIC publications, feel free to scan this QR code. And then I'm happy to take any questions. Thank you.